Okay, let's have the solution of example 15 point B. For maximum moment calculations for interior beam is WL square over 8, where W for interior beam is 19.52, length is 9 square divided by 8. So maximum moment for interior beam is 197.64 kilonewton meter. For an exterior beam, the load is 10.02, so 10.02 times 9 square over 8. So the maximum moment in the exterior beam is 101.45 kilonewton meter. For the interior girder, the loading is the uniform weight of the girder. Then we have a concentrated load at the center, which is 2 times the reaction of end reaction of the interior beam. The 2 times end reaction of the interior beam is 175.68. The uniform load is 0.98. So the maximum moment is equal to 0.98 times 7 square over 8 plus PL over 4. So 175.68 times 7 over 4 for the interior girder. 0.98 times 7 square over 8 plus 175.68 times 7 over 4. So maximum moment for the interior girder is 313.44 kilonewton meter. Maximum moment for the exterior girder, so the loading is weight of the girder 0.98 kilonewton per meter, and just the internal just the end reaction of the interior beam. So it is half of 175.68, so 187.84. So the maximum moment is 0.98 times 7 square over 8 plus 87.84 times 7 over 4. So 159.73. So let's proceed to the situation where S is 5.4. So this time L over S, 9 over 5.4 is less than 2. And therefore we have two-way distribution of the load. So we say two-way distribution of the load, the girder will partially carry floor loads. And the technique is to draw 45-degree lines from the ends of the beam as well as from the end of the girder. So for this interior beam here, this would be the loading. We have 45 degrees line, 45 degrees line. Then also on the other side, 45, 45. Then for the exterior beam, it should be trapezoid. So the floor will be half of the floor in the interior beam. So it's half. Then for the girder, exterior girder, we have these triangular loadings. 2. For interior girder, it is the floor area would be double the floor area of the exterior girder. So that's the loading condition for the interior beam, exterior beam, interior girder, and exterior girder. So let's begin with the interior beam. So remember that the pressure is, so this is the interior beam. We have a trapezoidal loading. This is 2.7. So as you can see here, 45 degrees. So this is S over 2. So that's also S over 2. So S over 2, 5.4 over 2 is 2.7. So 9 minus 2.7 times 2 would be 3.6. So the length of this horizontal line is 3.6, and the intensity of the load, it consists of the uniform weight of the beam, which is 0.5124 kilonewton per meter. Then we have this trapezoidal loading. So pressure is 2.4 times 9.81 times 0.15 plus live load 1.9 kilopascal. So the pressure is 5.4316, if you can remember. And this 5.4316 is multiplied by S over 2 and S over 2 for the interior beam. So S and S is 5.4. So multiplying that by 5.4, that's the uniform load of the interior beam. Intensity of the uniform load for interior beam. So it is equal to 29.331 kilonewton per meter. So that's the loading for the interior beam. For the exterior beam, it is 5.44316 times 2.7 only. So the superimposed load. Then remember that the weight of the beam is not shown in this figure, but it is 0.5124 kilonewton per meter. So the reaction at the end of the interior beam would be equal to half of the weight of the beam, so 0.5124 times 9 over 2. Then one half of the area of the trapezoid. So the area of the trapezoid is also one half upper base, lower base times height. So that's why one half is 1/4. Upper base 3.6, lower base 9, and the height of the trapezoid is 29.331. So the reaction at the end of the interior beam is 94.698 kilonewtons. Then for the exterior beam, which is this, it's 5.4316 times. So this is the weight of the beam, uniform weight of the beam. We have a trapezoid, but the height is shorter. The height is half of the intensity of superimposed load for interior beam. So 3.6, and WEB external beam is 5.4316 times 2.7 only, because the distance from one side, this beam here, and that point is S over 2 or 2.7. So WE beam, external beam is 14.665 kilonewton per meter. Then the reaction is again half the weight of the beam, so 0.5124 times 9 over 2 plus 1/4 of one fourth of quantity 3.6 plus 9 times height 14.665. Again, 1/4 is one half of area of trapezoid, which is one half again. So that's why one half is 1/4. So REB is 48.501 kilonewtons. Then for the interior girder, the loading condition would be, we have two triangular loads times 2, so it is double this intensity here. Then we have also a concentrated load at the center of the girder. This is the girder, which is end reaction of the interior beam. Then for this interior beam, because this is also interior beam, we have end reaction of interior beam. So the interior reaction of the interior beam is 94.698. So times 2, that would be the concentrated load at the center of the interior girder. And we have also triangular load, two triangular loads with intensity equal to 29.331. This one, because that's S over 2, this is S over 2 also, so times S. So W for interior girder is 29.331. Then this one also is 29.331. Then we have a concentrated load at the center, which is 2 times 94.69. So solving for the reaction RIG, it is equal to the area of this triangle. That's just this one. It is transmitted there because the other triangle is there. And one half of this load, so it's 94.698 plus one half the weight of the girder, which is 0.98 times 9 times 10.8 over 2. So 0.98 times 10.8 over 2. So therefore, the reaction at the end of the interior girder, which is here and here, is equal to 179.184 kilonewtons. So for the exterior girder, which is one example is this, its load is the same as the interior girder, but the intensity is equal to 14.665 for the triangular load, and the load at the center is only the end reaction of the interior beam, which is 94.698. So this is 94.698 for the exterior. So exterior girder, this is the loading situation. The intensity of the triangular load is 14.665, and we have a load at the center of 94.698. Then the reaction at the end of the exterior girder is equal to one area of the triangle, which is 0.5 times, this is 5.4, half of 10.8 times 14.665 plus half of 94.698, then half of the weight of the beam, which is our girder rather, which is 0.98 times 10.8 over 2. So REG is 92.2365 kilonewtons. We can now analyze the total force in column 2. So at the left side is external reaction of the exterior beam, which is 92.2365. Same is true with the right side. So we have 92.2365 in the left side, 92.2365. This is an interior beam, so the force here is equal to the internal reaction of the interior beam, which was 94.698. So therefore, the force in column 2 is 2 times, by the way, the dimension would be 10.8, then this is 4.5. So 4.5, then 10.8. So therefore, force in column C2 is 2 times 92.2365 plus 94.698. So it is equal to 279.171 kilonewtons. So the other way of computing for the force in column 2 is to use the pressure and multiplied by that area plus the weight of the girder and beams. So remember that we have a beam here, and half of the weight of the beam, whose length is 4.5, is distributed to this column here. The other half is in column 1, C1. Then same is so there is a beam here because this is the center, and half is thrown here. The other half is thrown in column C3. So therefore, the length of the beam is 4.5, then half of 4.5 plus half of 4.5, that's 4.5. So the total length of the beam is like 9, because this is supposedly divided by 2, this is also divided by 2, so total length of the beam is 9, while the length of the girder is exactly 10.8. So remember, the pressure is 2.4 times 9.81 times thickness of the floor 0.15 plus live load 1.9, so it is 5.4316 kilopascals. Then you multiply that by the area, which is 10.8 times 4.5, then plus the weight of the beam, which is 0.5124 kilonewton per meter. The total length of the beam is 4.5, then half of 4.5 plus half of 4.5 is 4.5. So 4.5 plus 4.5 is 9. Then plus the weight of the girder, 0.98 times the length of the girder is 10.8. So you will get the same value of 279.171 kilonewtons. Now for column A3, this is column E3 here, then the dimension will be 4.5 and half only of 10.8, so 5.4. And we have the reaction here, which is, this is an exterior beam. So the force here would be, or the reaction here would be reaction of the exterior beam. The reaction of the exterior beam is equal to uniform load of the exterior beam, or we already computed that from the preceding slides. It was 48.501. Then this is the end reaction of the exterior girder, and the exterior girder end reaction is 92.2365. So that's 92.2365 Therefore, the force in column A3 is 48.501 plus 92.2365. And that is equal to 140.738 kilonewtons. Then, if you use the pressure, so it is equal to 5.4316 times the area, 5.4 times 4.5. The length of this beam is whole 4.5. It will be uh, transmitted to column E3. So 0.5124 times 4.5. We also have a beam here. Half of that weight is transmitted to column E3. The other half is transmitted to column E2. So we only compute the weight of this beam, and half of its weight is transmitted to column E3. So this is, we write 0.5124 again, divide by 2 times 4.5. Then weight of the girder is 0.98 times 5.4, obviously. So force in column A3 is equal to 140.738, which is equal to that. So next is the maximum moment. So for beams, we can use the suggested formula. We can also compute the moment of the beam based on the actual loading. And we can check it using the formula. But for the girder, because of the complicated loading, we have two triangles, we will not use the formula. Equivalent load formula. So this is an interior beam. This is the weight of the interior beam is 0.5124. It's uniform. Then let's convert this trapezoidal loading into uniform loading. Its original value was 29.331. If we convert that to a rectangular loading, it should be lesser than 29.331. So the formula was for long span is PS over 6 times quantity 3 minus quantity S over L closed square. Then we will multiply the equivalent uniform load by 2 because for the interior beam, remember that there are two sides, two floor area, left side and right side. So that's why we multiply the formula by 2. And the weight of the beam is separated. So this is the pressure, this is the S, 5.4 over 6, then 3 minus S over L quantity square, remember the formula. Then we multiply the whole of this value by 2 because this is an interior beam. There are two equal sides of the interior beam. So you multiply that by 2. Then don't forget to add the weight of the beam, which is already uniform, 0.5124. So the equivalent uniform load in the interior beam is 26.323 kilonewton meter. So you just imagine that the beam is converted into the one that is loaded with uniform load of intensity 26.323. And because this is simply supported beam, the maximum moment at the center is WL square over 8. And W is 26.323 times 9 square over 8. So it is equal to 266.52 kilonewton meter. If you are not given by that equivalent formula, can we still compute the moment at the center, the maximum moment in the interior beam? Yes, we can still compute it based on the actual loading. So all you have to do is cut at the center, then consider the left side, take moment at the center. The maximum moment should also be 266.52. So we already computed RIB. So the distance of RIB from the center is 4.5. Then we subtract the moment of this rectangular load, which is 29.331 times, of course, 1.8, half of 3.6. Then the moment arm is 0.9. Then minus the moment of this triangular load, which is 1 half of 2.7 times 29.331. The moment arm is 1/3 of 2.7, which is 0.9 plus 1.8, half of 3.6 is 1.8, so 2.7 also. Then minus the moment of this weight of the beam, which is 0.5124 times 4.5 times half of 4.5, 2.25. So that is RIB is 94.698 times 4.5. Then subtract the moment of this triangle, which is 1 half or 0.5. The base is 2.7. The height is 29.21. I hope you can follow. Then the moment arm is 1/3 of 2.7 is 0.9 plus 1.8 half of 3.6, so 2.7. Then minus the moment of the weight, uniform weight of the beam, which is 0.5124, minus 29.331 times 1.8 times 0.9, this rectangular loading, then minus the weight of the beam, 0.5124 uniform times 4.5, the area of the triangle, then the moment arm is half of 4.5, which is 2.25. So if you compute that, that's also 266.52 kilonewton meter. So it doesn't matter if you're given with the formula or not. The maximum moment can still be computed based on the diagram. Then for the maximum moment in exterior beam, so we have this loading. REB is 48.501, remember, for the exterior beam. Then we have trapezoidal loading, same as this except the intensity, which is 14.665. So we compute the equivalent uniform load according to the formula. We will not multiply this formula here by 2 anymore because this is an exterior beam. So there's only one side where there is loaded area or loaded floor. So W equivalent of the exterior beam is equal to pressure times 5S 5.4 over 6 quantity 3 minus S over L quantity square. So there's no more times 2 because it is an exterior beam plus the weight of the beam itself. So W equivalent for the exterior beam is 13.418. So knowing that equivalent uniform load, then the maximum moment at the center is WL square over 8 again. So 13.418 times 9 square over 8. So it is 135.86 kilonewton meter. Then for the exterior girder, so I need to compute the maximum moment for exterior girder. But before that, let's compute the moment at the center for an exterior beam based on its loading. So it is REB, which is 48.501 times 4.5 minus the moment of this moment of the triangle, which is 0.5 times 2.7 times 14.665. The moment arm is 1/3 of 2.7 is 0.9 plus 1.8, so 2.7 again, minus the moment of the uniform load, which is 14.665. The length is only 1.8, half of 3.6, then the moment arm 0.9, then minus the moment of the weight of the beam, which is 0.5124 times 4.5 times 2.55. So calculating this value, it should also be equal to 135.86 kilonewton meter. Then for the exterior girder, you can see the loading here. We cannot use equivalent load method anymore because there is a concentrated load at the midspan. So instead, we compute the moment at the center of the exterior girder where maximum moment occurs by the basic method. That is, we simply sum up moment about the exterior girder. Anyway, we know already this is 92.2365. Its distance from the center is 5.4. Then minus the moment of this triangular load. The moment arm is 2.7 because this is an isosceles triangular loading. Then minus the weight of the girder, which is 0.98 Moment of the weight of the girder is 0.98 times 5.4 times 2.7. So that's it. So maximum moment exterior girder is 92.2365 times 5.4 minus the moment of this triangular loading, one half is 0.5, 5.4 horizontal distance, height 14.665, and the moment arm is half of 5.4 or 2.7. Then minus the moment of the uniform weight of the girder, which is 0.98 times 5.4 times 2.7. So the maximum moment in the exterior girder is equal to 376.88 kilonewton meter, and the maximum moment in the interior girder, which I just calculated it. Then you check this in your you check this in your free time. Uh, it's the same as this loading here, except this intensity of the loading, which is 29.331. So the procedure is the same, the moment arm is the same, except that you change this value here. And of course, the reaction at the end of the interior girder is different. It's not 92.2365. So show that the maximum moment in the interior girder is 739.48 kilonewton meter. And that's it. And I hope you are able to follow the solution. If not, then repeat viewing the solution, because this is in video format. So you can continue, you can repeat the viewing of the solution so that you can understand.